Rogers Dry Lake, California, in the Mojave Desert. 64 square miles of sun-baked concrete hard dry lake bed. A hostile environment. Yet some of the world's most brilliant scientists, engineers, and test pilots have been lured into this scorched, sprawling desert. Offering the largest natural runway in the world, this lake bed is now a part of Edwards Air Force Base and has earned its place in aviation history as the home of a unique family of purely experimental aircraft, the X-planes. The latest in the long line of the X family, the X-31 is designed to explore exciting new areas of aircraft maneuverability. Like all of its predecessors, it thrives in the regions of the unknown, opening new frontiers for science and technology. The very first of the X-planes was the Bell X-1, conceived and built in the years after World War II. In its time, it was the strongest aircraft ever constructed. It was built to withstand mysterious forces that would tear apart lesser aircraft. The X-1 was to be flown faster than any plane had gone, faster than the speed of sound, into the unknown realms of supersonic flight. Air-launched from the bomb bay of a B-29, the X-1, in a series of carefully metered test flights during the late 1940s, would creep closer and closer towards that goal. To achieve this, the little aircraft would have to pass through what many theorized was an unpassable wall of buffeting and strange shock waves thought to render controlled flight impossible. This wall was named the sound barrier, but if any aircraft could punch its way through, it was the X-1. J. Miller, aviation author.
This period of aviation, the late 1940s, the post-World War II period up through the mid and late 1950s was, aerodynamics, especially transonic and supersonic aerodynamics, were at a very seminal stage. The difficulties that lay ahead were simply unknown.
The solely experimental X-planes were flying laboratories working at the hazy edges of aeronautical knowledge. Built to fly beyond Mach 3 times the speed of sound, the X-2 was to enter the flying hell of the thermal barrier, where a lesser aircraft would have burnt to a cinder. The sleek X-3 Stiletto revolutionized the method of building aircraft and became instrumental in unlocking a mysterious chapter in aerodynamic theory, saving many lives. Northrop's tiny X-4 Bantam was built to explore the tailless aircraft configuration. Experience invaluable in developing similar configurations, including the B-2 stealth bomber. Bell's X-5 could change the sweep of its wings in flight, allowing it to perform at high and low speeds, paving the way for aircraft like the F-111 and F-14 Tomcat. The Convair X-6 project was to test the concept of a nuclear-powered bomber. Initial proving flights were executed using the specially converted NB-36H, which carried aloft a nuclear reactor in its bomb bay. Many of the X projects studied vertical flight, the Bell X-14 using early thrust vectoring and reaction control systems. The X-13 Vertijet sat on its tail for takeoff and landing. The X-22 used a novel approach of ducted fans to explore vertical takeoff. In one of the most successful X projects, the X-15 took pilots so high they edged into space. Still the fastest conventional winged aircraft flown, the X-15 reached an incredible speed of over 4,500 miles per hour in 1967. Looking as if it would never fly, the strange X-24B was part of a series of lifting body aircraft that helped in developing new flight concepts used throughout the Space Shuttle Orbiter program. Here we see one of the latest X-planes, the X-29. exploring the novel forward-swept wing configuration, giving it never-before-seen maneuverability. The X-planes, one and all, stand alone as symbols of the extraordinary.
They are, from an aesthetic standpoint and in terms of what they've accomplished in terms of performance, they are, to this very day, they are the fastest and highest flying conventional fixed-wing vehicles that have ever been built.
Extraordinary planes demand extraordinary pilots to fly them. So the X-plane story is also about the daring men who flew these aircraft where no man has ever gone before. Our story also highlights the technologists that designed these aircraft as windows into the future. The contributions of these brave and brilliant individuals have made possible amazing advances in aviation, paving the way to the new frontiers of space. Modern combat jets like this F-15 fighter fly faster than the speed of sound as a matter of course, their high performance beholden to a legacy, to the early X-planes that proved that supersonic flight was possible. As far back as World War II, even pilots flying this moderately fast Bell P-63 fighter began to experience severe buffeting during high-speed dives when approaching 500 miles per hour. Many believed there existed an invisible wall through which aircraft could not pass.
Some of the best fighters of that period, certainly the P-51, the P-38 in this country, began to encounter the problem of compressibility. And this happened frequently in high-speed dives. When they get into the transonic region, that is speeds above about 0.8 Mach, speeds approaching 500 miles per hour, the airplanes would be in a steep dive, picking up speed, enter this region, and all of a sudden pilots would find that their flight controls were freezing up or completely ineffective. And they found it impossible to pull out of these dives on many occasions.
Molecules of air not able to move out of the way fast enough were being compressed in front of the aircraft. Shock waves moved back along the aircraft the faster it went, disabling the flying surfaces, making the aircraft uncontrollable, thus creating an almost impenetrable wall at higher and higher speeds. By the 1940s, propeller-driven aircraft were at the outer limits of their performance, so other answers were sought to gain speed. Almost at the same time, the Allies and the Third Reich came to similar conclusions. British and German jet technology introduced new frontiers of high speed. With a top speed of 540 miles per hour, the Messerschmitt Me-262 had a 100-mile-per-hour advantage on any Allied aircraft of the day. Its revolutionary power plant was married with a moderately swept wing, making it, for a time, the world's most formidable fighter. Even more spectacular, the Messerschmitt Me-163 Comet. This tiny, tailless, swept-back aircraft was rocket-powered. Used against the Allied mass bomber formations in the closing stages of the war, it became the fastest operational aircraft of World War II. This incredible fighter could climb at a rate of 14,000 feet per minute. But after only 10 minutes flying time, fuel exhausted, it would have to glide back to base for an unpowered landing. In 1941, the Me-163 secretly became the first aircraft to exceed 1,000 kilometers an hour, making pilot Heini Dittmar the fastest man on Earth. But the Me-163's designer, Dr. Alexander Lippisch, had not built the little rocket fighter for supersonic flight. However, towards the end of the war, Lippisch did draw plans for a supersonic delta wing aircraft. The V-2 rocket, although not piloted, proved that a man-made craft could be successfully propelled into supersonic flight. As the V-2 rose from its launch site, a strange cracking noise was heard in the sky. Ground observers were hearing a massive compression of air molecules. The world's first man-made sonic boom. But the V-2 was a ballistic missile. It didn't need to be maneuverable because it wasn't built to be piloted. The question remained, could man fly an aircraft at sonic speeds and control it through the gray area, the wall?
The gray area didn't actually lie in the area of supersonic speeds. The gray area lay in the transonic zone. In other words, in between subsonic and supersonic velocities. It was that transitional period between subsonic and supersonic velocities where they really didn't know for sure what was going to happen.
After the war, much was learned from captured German technology. The Me-262, V-2, and the Comet were studied in detail. Slowly, German advances were blended with Allied technology to forge new aeronautical developments in the post-war age. Almost from the beginning, wind tunnels had been used to test aircraft flight characteristics, and by the 1940s had become an exacting science. But technologists began to notice strange phenomena as they tried testing airflows approaching the speed of sound. In these uncharted regions, the faithful wind tunnel proved to be of little use. It seemed the only way through the wall would be to build aircraft and have men fly them.
One of the things that they ran into in wind tunnels was a choking phenomenon. Basically, they were having difficulty ramming supersonic air through a wind tunnel in such a way that the air was stable, and it was a continuous, very steady flow. A choking phenomenon would take place, which basically was a buildup of shock waves inside of the wind tunnel. As a result of that, the results they were getting from wind tunnel studies at supersonic speeds were ambiguous. In other words, it was not easily discerned as to whether or not the information was accurate and whether or not it accurately portrayed an event that would take place, let's say, when you're actually flying through the atmosphere at supersonic speeds.
Augmented with lessons learned from captured German technology, the British took a lead in the race to the wall with its early jets fathered by Frank Whittle. Britain's de Havilland Vampire was used as the starting point for a truly exciting new experimental jet aircraft design. This new plane would have wide sweeping wings, but the distinctive twin tail boom of the Vampire would be replaced with a vertical fin, leaving no horizontal tail at all. It would explore the transonic speed range. The emerging DH-108 Swallow looked strikingly like the Me-163. Designers hoped the tailless configuration would carry Britain into the supersonic age. But in September 1946, the Swallow project was dealt a fatal blow. British test pilot Captain Eric Brown recalls.
Geoffrey de Havilland Jr., who was chief test pilot for the company, was working up towards this, and he had been making runs at around about medium levels of 10,000 feet. And this particular day, he brought the aircraft down to 7,000 feet and made a run at about 0.875 Mach number. And at that speed, the aircraft suddenly disintegrated. He was thrown out, never opened his parachute, and his body was found in the mud flats of the Thames estuary.
Focus now shifted to the hot and dry lake bed, high in California's Mojave Desert, near a town once called Muroc. In 1948, Muroc and the surrounding area became Edwards Air Force Base and remains today the premier research flight center in the U.S. But at the turn of the century, there was literally nothing there. Back in 1910, the Coram brothers, Ralph and Clifford, settled here, drilled for water, then built a small community. Soon there was a train station, post office, church, and general store on the edge of Rogers Dry Lake. To avoid confusion with another town, it was christened Muroc, Coram spelled backwards. Years later, between the two world wars, the Navy denied the Army Air Corps permission to use the Pacific for aerial bombing practice. In its search for an alternate range, the Air Corps discovered this dry lake with its isolated natural landing strip and year-round flying weather, making it a perfect practice location for then and into the future. The Air Corps set up base during the early 30s, and by 1937 the range was being used on a regular basis. During World War II, the base continued as a bombing range, with the Army building a curious target out on the dry lake. Dr. Jim Young, Edwards historian.
The Muroc Maru was a 650-foot mock-up of a Japanese Mogami-class battle cruiser. It was erected out on the lake bed, and it was used by bombing crews to practice the tactics of skip bombing. And there are a lot of interesting occurrences, apparently. During the summertime, there's a shimmering out on the lake bed, so that if you look at it in certain angles, it actually looks like there's water on the lake bed. And there was a road that drove right next to the base throughout the war years, and travelers coming from the east, unfamiliar with the area, would pass by and see what they thought was a battleship on a lake in the middle of the desert. And the base got a lot of calls to the Public Information Office from people who thought they were hallucinating.
In 1941, the Air Force found itself in need of a remote location to secretly test fly the Bell XP-59, the United States' first jet aircraft.
Muroc had been selected for three very good reasons as the site for these tests. The most obvious, of course, was the existence of the lake bed. The isolation of the location was very, very important. This was a program which was kept in a top secret status until January of 1944. And of course, there were the crystal clear skies, the outstanding flying weather.
On October 1st, 1942, the XP-59, powered by two GE jet engines and flown by Bell test pilot Bob Stanley, slowly lifted off the hot, dry lake. Its engines were based on imported technology from Whittle in Britain. These flights were the beginning of the American jet age and marked the first of many new technological advances in the clear blue skies above the dry lake. As the world recovered from the horrors of the Second World War, Muroc's reputation grew as an obvious choice for a flight testing center. The most exciting test aircraft in the world in 1946 was the Bell X-1, built to withstand the unknown forces of transonic flight. Test pilot Chalmers Slick Goodland was the first man to fly the X-1 under power.
Well, there were all sorts of stories about crossing the sound barrier being very destructive. In fact, as you know, Jeffrey de Havilland was lost in an airplane attacking the sound barrier, and they said it just came apart and disintegrated because of the forces in attempting to go through the barrier. And there were a lot of stories floating about that it was extremely difficult, so they simply built the aircraft to withstand tremendous forces.
Eager to keep the X-1 under wraps, the Army Air Force searched the country for a suitable base for the X-1 test flight program. Although its first glide flight tests were completed at Pine Castle, Florida, the isolation and year-round flying weather and the dry lake's very long emergency landing strip won Muroc the permanent test site honor.
The speed of sound, to a lot of people, was a barrier, a sound barrier that couldn't be broken. But a great many people around the country, and certainly those involved in the X-1 program, didn't think of it as a barrier. They really thought of supersonic flight really more as a steep hill. They were quite confident that they could do it. It was just a matter of when.
In a series of carefully monitored test flights, the X-1 was flown closer and closer towards Mach 1. At the other side of that steep hill, a new era awaited. Through the invisible wall lay the tantalizing dream of supersonic flight.
At the Filton BOAC factory in Bristol, British workers laboured on Concorde 002. Because of the Anglo-French double production line, a new way of manufacturing aircraft came into being. Previously, aeroplanes had been assembled as a shell, then components inserted inside. With the Concorde, many of the systems were installed at the component stage, then brought to the assembly line already functional. This was the case with the nose and forward fuselage built at Weybridge. The 50-foot-long section was made up of the flight deck, the forward passenger cabin, and the nose landing gear bay. When brought to the final assembly line, the sections were fitted with cabin insulation, hydraulics, and air conditioning, comprising 25,000 parts and 90 miles of wiring.
We have a camera specially rigged on the tail to give you a close-up view of what happens when you break the sound barrier. Let me tell you what to watch for. First, notice the deep color of the sky, how much darker it is at 45,000 feet where Tony will start his dive. You are not only far above the clouds, but also above the haze and dust of the lower atmosphere. You are looking at the pure ultraviolet rays of outer space. There's the peel off. Now listen as the sound builds up. Usually, there are two thunderclaps. One when the plane runs away from its sound, and the second when the sound catches up again. Between the two, you are flying faster than the speed of sound, and it is absolutely silent. Now the sound is building up. The sound barrier has been broken. This is the silence of supersonic flight. Now the pullout is being made. Listen to the noise when the sound catches up.
A bevy of air hostesses gathered at the Paris Air Show in 1967 to usher in a new era of passenger flight. At the center of attention was an aeroplane born from unprecedented cooperation between traditional rivals Britain and France. Christened Concorde, it was well named.
A beautiful shape of things to come. A model of the Anglo-French Concorde airliner to be carrying 100 passengers by 1970. At Lancaster House, the aviation minister, Mr. Julian Amery, in company with the French ambassador, almost crooned in admiration over the brainchild of their two countries. On behalf of their governments, they signed the agreement for the joint development and production, a foretaste perhaps of common market cooperation. Concorde has a perfect pedigree. In the early days, the Fairy Delta II proved faster than sound flying to be possible. Then the French Trident, powered by two jets and a rocket motor, flew twice the speed of sound. At the Bedford Wind Tunnel, flight conditions at these fantastic speeds are simulated, a tremendous help to the designers of the airframe, in this case a model of the Concorde. Watching is the head of the Bristol design team of the British Aviation Corporation. On the testbed here, a Bristol Siddeley Olympus engine, the type that will power the Concorde. The same engine has been tested in flight, powering a Vulcan bomber. The Handley Page 115 demonstrated the possibility of handling the slender delta-wing aircraft at low speed. More tests were made by the Bristol T-188 Flying Laboratory. With a pedigree like that, the Concorde should capture a big slice of the Atlantic traffic for Britain and France.
Britain first started working on civilian faster-than-sound aircraft in the mid-1950s, when the Bristol Aeroplane Company developed the Type 233 supersonic jet. At the same time, France's Sud Aviation was working on the Super Caravelle, so in 1962, the two nations joined forces. Partly a reaction against the swift technological strides being taken by the Russians and Americans in their duel to reach the moon, the Anglo-French partnership was negotiated as an international treaty rather than a commercial agreement. But the project was not without controversy. The name itself was initially a bone of contention. Although the British originally spelt it with an E in the French style, British Prime Minister Harold Macmillan took offence at a comment from French leader Charles de Gaulle and ordered it to be spelt without the E. Eventually, British Minister for Technology Tony Benn proclaimed that the French spelling would be adopted by both countries, saying the E stood for Excellence, England, Europe and Entente. He subsequently received a letter from an angry Scot who said the Concorde was made in Scotland as well as England. Ben responded that the E could stand for Écosse, the French name for Scotland, but in his memoirs he noted, and I might have added E for extravagance and E for escalation as well. For it was a massive project, and both sides underestimated the complexities involved. Britain was to construct 60% of the engine and 40% of the airframe, and France to construct 40% of the engine and 60% of the airframe. But with Concorde unlike any aeroplane previously built, the project stretched out long past its due date and chewed up far more than its allotted budget.
We're very glad to have you with us this evening because you, as the Chief Executive and General Manager of Qantas, Australia's overseas airline, obviously the very person to tell us something about this, the background to this quite momentous news about the authority that has been given to your airline to negotiate for 10 supersonic airliners. This seems to me to be pretty exciting news, and we'd like to hear you tell us something about it.
Thank you, Mr. Gillison. It is exciting news. We've been working on the supersonic transport project for 2 years, like many other airlines, and this is the culmination of much work. Although we've only, at the moment, got permission, as you'll see, to pay deposits to secure positions in the line. There's very much more work and negotiation to be done in relation to the US SST, as we call it, supersonic transport. There's actually no defined aircraft at the moment, and we're paying deposits in the dark. We are also, of course, enthusiastic about the Concorde, British-French project, and that we've got authority to pay deposits on 4 of those is very encouraging news for us. But there's, as I say, there's much negotiation to be done.
Well, what about this authority to negotiate for 6 American airliners? There is the picture there.
Of course, the American airliner, supersonic airliner, is not yet an airliner. It's being decided about this time, and we'll know more about it within the next few months. But what we are doing there is paying deposits to secure positions in the future line. But then, in that case, if we don't want to go on with it by the end of 1965, if it doesn't meet our specifications, we get the whole of the deposit back. In this instance, in this way, it is vitally different to the type of contract that we are at the moment discussing with BAC Sud.
Across the Atlantic, the United States had been developing its own supersonic airliner, the Boeing 2707, or Supersonic Transport, SST. Boeing won a competition to build the jet in 1960. The announcement that Britain and France had combined forces to develop the Concorde put the nail in the coffin for the SST, as there was little evidence of enough demand for the Concorde, let alone another supersonic airliner. However, in the interests of American aeronautical development and superpower pride, work on the SST continued for several years. It underwent many different incarnations, including a variable geometry wing, later abandoned for a tailed delta wing. Some SST supporters dreamed of a sky populated by supersonic airliners, believing the 747 was a passing fad. Not to be outdone, the Russians pushed ahead with their own supersonic airliner, the Tupolev Tu-144, challenging Concorde in some areas of technology, but lacking Concorde's range, sophistication, braking and engine control. Despite many roadblocks, the Concorde Vision flew on, with a model taking to the air for flight tests in 1966. The program was feeling some urgency because of the Boeing supersonic developments. But Concorde's designers were also convinced that the American plans were far too ambitious to be achieved in less than a decade. The SST was to have a speed of Mach 3, be constructed from titanium, and stretch at least 330 feet long, the length of a football field. A little more modest in scope, the Concorde could reach Mach 2.04, or 2,200 kilometers an hour, and was constructed from aluminium in a relatively conventional design compared to the SST. Its maximum cruise altitude was to be 60,000 feet, and average landing speed 298 kilometers an hour. Dangled below a helicopter on its test flight at the Royal Aircraft Establishment near Bedford, this model was only 1/20th the size of the real aircraft. Although it was attached to the helicopter by a tow rope, the model was controlled independently and could lift, roll and turn, while recording instruments measured its performance. It also had a few moments of free flight. There were many structural issues to be considered in an aeroplane that was traveling at twice the speed of sound. With massive forces applied to the aircraft during banks and turns, the outboard elevons were neutralized at high speeds, leaving only the inner elevons active as they were attached to the strongest part of the wing. At this point in its development, more than 20 research establishments in Britain and France were working on the aircraft, and the budget had climbed to £380 million sterling. Gradually, its parts started to take shape in workshops on both sides of the Channel. At the Hispano-Suiza factory in Paris, workers constructed the undercarriage of the prototype Concorde 001. It rested on a four-wheel bogie, standing 4 meters from the point of retraction to the bogie axis. Development of the Concorde was a leap into the unknown for designers and engineers. The machine and assembly shops built test specimens of the advanced RR58 aluminium alloy to ensure it could be fabricated using tried and true techniques. Titanium and stainless steel were also used in the engine bays to combat the high stress and high temperatures. Electron beam welding was perfected to enable production welding of the titanium, previously a very difficult task. In 1967, the design for the 001 and 002 prototypes was revised to reduce drag. The Concorde received a new drooping nose and visor and a longer fuselage. The trademark drooping nose gave the pilots increased visibility when the delta-winged aircraft took off and landed at a high angle of attack. When in flight, the nose was raised to horizontal to allow for aerodynamic streamlining through the air. There was no end to the ingenuity or patience of the Concorde designers. They undertook photographic analysis using Polaroid light to pinpoint the stresses that pressurization forces exert on welds. They carried out experiments to test the effects of kinetic heating on exterior paintwork and the effects of 40,000 hours of wear on seating fabrics. The designers called on the power of analog computers to measure and record the drag forces at various points of an aircraft wing during a simulated flight. And they carried out experiments in wind tunnels that were like test flights in miniature. With this model, aerodynamicists could study Concorde performance in every phase of flight, from takeoff to landing. When they came to cutting the metal used in the airplane, a process known as sculpture milling was used. In this process, 90% of the original material is machined away to be salvaged and used again. It was a costly method, but faster than any other, ensuring the structural integrity of the parts produced. Magnetic control of the machining operations ensured maximum speed and maximum accuracy, however complex the component. Chemi-etching, another advanced technique, was used to produce components. Forming was done by successive immersions in acid. During immersion, the parts that will finally stand out in relief are protected. The first components to come off the assembly lines in Britain and France were assembled into fuselage sections for extensive structural testing. The components also underwent fatigue testing, where cyclic loadings were imposed on the specimen to simulate the stress and strain of actual flight. For air conditioning tests, a fuselage section was encased in a high-altitude chamber. To check the efficiency of the cabin cooling system, thermocouples took the temperature of the metal passengers. But not everyone was enamored with the technological milestones being reached through the Concorde program. In 1966, a saboteur smashed an important engine part at the Bristol Siddeley aircraft factory in Bristol. The smashed engine part was found with a hammer lying nearby and a note that read, "This is the mallet which did the job. I wish I could be here to see the fun." Both workers and management were furious at the sabotage and resolved not to let the incident disrupt their schedule. The aeroplane was due to be delivered 21 months later. Although the sabotage meant the Olympus 593 engine would be affected, factory management was adamant that the Concorde would meet its delivery date. However, the project was already running behind schedule. This was less to do with sabotage and more to do with the complex collaboration between engineers from different countries. There were constant problems with getting on-time delivery from outside contractors, mostly because of the extensive testing required before the materials could be used on the Concorde. To distract attention from what was rapidly becoming a costly and delayed operation, the British trumpeted the opening of a super wind tunnel. When the time came for Concorde to make its first test flight, it was a momentous experience. Technology Minister Tony Benn remembered it as quite extraordinary. It was typically British and extraordinarily exciting, and I must say that when I took off, the vibration made me feel like I was being filleted, my skin falling off my skeleton, he said. I did arrange for a supersonic bang to take place over Cabinet, and I told the Prime Minister and no one else. Ben sat behind the pilots wearing a parachute and filming the occasion. He next flew on the aircraft in 1976 with a group of people who had worked on its construction for 20 or 30 years but had never previously had the opportunity to fly in the luxury jet. Many tests were carried out on the new aeroplanes, including a slate of noise tests. Engineer Dick Hale, a member of the Weybridge Acoustics Department, was one of those who worked on the experiments. At first, engine tests were conducted close to the assembly building. Later, a custom-built ground base was built next to the yet-to-be-operational runway. There were 6 in the BAC team, all in our early 20s, our team leader being just 24, Hale recalled. I was a new qualified engineer, just 6 months out of my apprenticeship, and helped set up the equipment, calibrate it, and operate the recording amplifiers and tape deck. The measurements were made around a 60-meter radius centered on the port side engines and covered an angular range from 25 to 180 degrees to jet exhaust. These relatively close-in measurements were to minimize the effects of wind and temperature gradients on noise propagation. The weather conditions were far from ideal, with plenty of wind and rain. The ground over which the microphone cables were laid was sodden, and the damp wormed its way into much of the measuring equipment, causing numerous reliability problems. However, after 3 to 4 weeks of intermittent testing, a full set of recordings were obtained, which included single and multi-engine running, operation of the Snecma Spade silencers, and qualification of the fixed ground running silencers. The recorded data formed a base for in-flight projections and the study of installation effects of closely coupled engines. Hale said his most embarrassing moment occurred when he was waiting to record the first ever installed engine reheat run. Our French colleagues indicated on the radio that the afterburner was lit. We hit the record button and the mains power to our test equipment dropped out. We looked out of the recording caravan window to see the mains cable flapping in the exhaust of the Olympus engine. At this high power setting, the ground covering the mains cable was eroded by the engine exhaust, exposing the cable and pulling it from the junction box. We buried it deeper next time. The extent of Concorde testing and certification was unique in the history of aviation. The prototype, pre-production and first production aircraft undertook 5,335 flight hours, 2,000 of which were supersonic. It went through 4 times as many tests as a standard aircraft. The first 4 Concorde aircraft were really flying laboratories, wired up with 12 tons of electric test instrumentation capable of recording measurements of 3,000 different parameters, including pressures, temperatures, accelerations, and attitudes. This information was recorded to magnetic tape for later analysis at ground data processing centers. In flight, certain information was cabled down to ground monitoring stations. At the front of each aircraft, there was room for 3 flight observers who monitored the behavior of the airplane and its systems through instruments duplicating the information appearing on the flight deck. One of the most important tests was flutter testing, where vibrations occurring in one part of an airplane can set off vibrations in another part, potentially leading to structural failure. But, not surprisingly, the extensive testing caused a budget blowout by the end of the process. Originally slated to cost £380 million sterling, the cost had rocketed to more than £1 billion by 1976, when the aeroplane made its first scheduled passenger flights. On October 1, 1969, Concorde 001 reached a milestone when it flew at supersonic speeds for the first time, achieving Mach 1.5 and flying supersonically for 9 minutes. Those on board were astonished at the absence of noise when the visor was raised. Only 7 months after that flight, 4 airline captains were given the opportunity to fly Concorde 001. The men trained in the Toulouse Concorde flight simulator and tried out many predicaments, including engine failure and a 3-engine landing. They later reported the aircraft was simple to fly, and they could see no reason why pilots and engineers couldn't be trained to operate it. The following year, both prototypes reached Mach 2 and passed 300 hours flying time. It was really looking as if supersonic passenger flight was possible. While the military had been flying at supersonic levels for many years, to construct an aircraft capable of sustaining the high structure temperature required for sustained flight was no easy task. Most of Concorde's test flights were flown over sea. However, the British government set up special provisions to enable the aeroplanes to occasionally fly over land as well. A route was designed over Scotland, Wales, and Ireland, carefully planned to remain within the range of air and ground rescue services. Fortunately, they were not required, but some people were disturbed by the startling sonic boom that would unexpectedly explode from the airplane as it crashed through the sound barrier. The first serious incident in the Concorde program occurred in January 1971, when 001 experienced an engine surge while flying at supersonic speed. One of the movable ramps in the engine air intake broke free, and metal fragments were ingested by the engine, causing a large amount of damage. The engine was immediately shut down, and 001 returned to Toulouse on 3 engines. The problem was fixed and never returned. Throughout 1971, 001 and 002 toured the world, thrilling people with their exploits. 001 made 16 flights in 15 days to places such as Rio de Janeiro, São Paulo, and Buenos Aires. Distinguished guests who tried out the cutting-edge aeroplanes included President Pompidou of France and the Duke of Edinburgh. A trained pilot himself, the Duke even took over the controls for part of his flight. To rub salt into the wounds of the struggling American supersonic program, Concorde soon roared into the United States, arriving at the nation's capital to lobby for landing rights in the U.S. Some Americans were virulently against allowing Concorde to fly into the United States, citing noise and air pollution concerns. The publicity tour saw the supersonic airliner carrying a plane load of big-name personalities, including senators and congressmen, over Mexico to demonstrate the sensation of flying at twice the speed of sound. It was a smart move and opened many doors for the airliner. The public was fascinated with the jet, flocking to airports to watch it take off and land. It was a sad contrast to the Boeing SST project that had, as its Concorde rivals suspected, never got off the ground. It was simply too grandiose a plan to be implemented in reality.
We expect to be in service in early 1978. This is based on getting approximately a year's flying experience with the prototype prior to a start of the production program.
So that would put it about 5 years behind Concorde.
Well, it depends on when you decide the Concorde goes into service. I think it's more important myself to talk about the difference in first flight dates, so I will only admit to the difference between the first flight of the Concorde this year and our first flight in 1972.
However, the American SST program was discontinued in 1971, following protests from environmental groups concerned that SST engine exhaust would damage the ozone layer or disturb people with sonic booms. But even without the protests, it's highly unlikely that the SST was a practical or realistic transportation option. Initially, there had been some concern in Britain that, as with the Comet, its engineers would pioneer new aviation technology only to see the Americans take off with it and race ahead, locking down the market. However, as the droop-nose Concorde powered through the skies, there was no sign of its American competitor. It was a full 5 years ahead and planned to make the most of its unfettered opportunity. The extra lead time would give the Anglo-French airliner a chance to prove itself in the competitive transatlantic market. Concorde's beautiful design made it a crowd favorite and gave it great prestige and glamour. It was a symbol of a new aviation age. When it flew through the air, it was so fast that other airplanes appeared to be flying backwards. In fact, it flew so fast that the weight of everyone on board was reduced by about 1% when flying east, the result of centrifugal forces. In 1976, British Airways became the first airline to take possession of a Concorde. The 200-foot-long delta-wing aircraft was handed over by the British Aircraft Corporation to British Airways Managing Director Henry Marking just 6 days before the aeroplane was scheduled to make its first passenger flight. British Airways flew the Concorde to Bahrain for its inaugural flight, while Air France flew to Rio de Janeiro. The Concorde was a revolution in flight time, slashing the journey time from London to New York from 7 to 3.5 hours. London to Tokyo was reduced from 14 3/4 to 6 3/4 hours. London to Sydney shrank from 24 hours to 13. One aspect of the Concorde's design that surprised many people was the small size of its interior. There was only room for 100 seats, 40 at the front and 60 at the back, and no space for overhead storage, severely limiting cabin baggage. The seats were narrower than most first-class seats on conventional airliners, but as the Concorde only flew during the day and arrived at its destination so quickly, the smaller seats were not an issue for most passengers. Concorde was powered by 4 Rolls-Royce Snecma Olympus 593 engines, which produced 38,000 pounds of thrust. They used reheat technology to add fuel to the final stage of the journey, giving extra power for takeoff and to jump to supersonic flight. Concorde's range was 4,143 miles, and the airliner could carry up to 26,286 gallons of fuel, consuming about 5,638 gallons an hour.
With the skyline of Australia's most famous city only 2 hours away, the crossing of the world's largest ocean at Mach 2 was rapidly becoming part of aviation history. Having crossed half the world in record-breaking time, realization of what we'd achieved started to set in. As the passengers continued to enjoy the buzz of Sydney, having covered a staggering 11,447 miles since departing New York, Concorde Alpha Delta was well due for a service. Whilst down under, there was no shortage of Qantas engineers volunteering for the task, under the watchful eye of BA's own Concorde technicians, the supersonic jet receiving a thorough check. With a warning light indicating a possible fault earlier, with one of the aircraft's inertial navigation system boxes, a new replacement was flown in especially from London, ready for Concorde's departure later in the day. 7 days into the trip and 4 sectors behind them, back in town, the passengers checked out of their luxury hotel for the 20-minute drive back to the departure gate at Sydney's main Kingsford Smith Airport. As they negotiated the Sydney freeways, the crew were already on the tarmac waiting for Concorde Alpha Delta's arrival from the hangar. As the aircraft was slowly towed along the web of airport taxiways towards the gate, with departure only an hour away, the race against time to fully prepare the supersonic jet for departure was to begin.
As Concorde's development was gathering pace, so was the Tupolev Tu-144. The Soviet supersonic aircraft flew many test flights and appeared to be achieving success. However, on June 3, 1973, disaster struck. While demonstrating its capabilities at the Paris Air Show, the first Tu-144S production airliner swerved into a violent downward dive. As it tried to pull out of it, the aeroplane broke up, then crashed, destroying 15 houses and killing all 6 people on board and 8 people on the ground. Debate still rages over the cause of the accident. One theory has it that the jet swerved to avoid a French spy plane that was attempting to photograph it. The original reports did not mention the presence of a Mirage military jet. However, later investigations acknowledged the Mirage, and one official statement said, though the inquiry established that there was no real risk of collision between the 2 aircraft, the Soviet pilot was likely to have been surprised. Meanwhile, Concorde forged ahead with plans to fly the transatlantic route, despite protests from some quarters. On November 22, 1977, Captain Brian Walpole piloted the jet from London to New York on the aeroplane's first fare-paying flight to that city. Pilot Peter Duffy was a British Airways Concorde captain from 1975 to 1980. In his book, Comets and Concords, he remembers training with test pilots, with exercises such as experiencing engine failure at Mach 2.02, more than twice the speed of sound. Spilled air from the intake caused an opposite reaction to what he had expected. Duffy also learned to handle the aircraft without auto-stabilization, demonstrating the Concorde's excellent basic stability. He was warned that it was easy to lose height when circling an airfield, because although the auto throttles set to control a specific airspeed did an accurate job, a small nose-down pitch could result in descent without the pilot realizing it. Duffy said smoothly landing the Concorde was possible through a simple technique. The delta wing produced considerable ground effect, and as the runway approached, it could be sensed as a cushioning feeling, as long as the descent was moderate. One journalist, Robert Hotz, editor of Aviation Week and Space Technology, described his flight in an editorial in the next issue of the magazine. The most sensational aspect of flying as a passenger at Mach 2 in a supersonic transport is that there are no sensations whatsoever that differ from those in the current generation of subsonic jets, he wrote. The only unusual internal noise comes during takeoff, briefly from engine rumble. The cabin noise level without full airline-style soundproofing is about equal to that of a current subsonic jet, with only a slight increase near the aft section. Cabin pressurization maintains a constant 6,500 feet environment, even during supersonic climb and descent. During Mach 2 maneuvers, only the changing color of the sky informs the passengers of major banking turns. It is possible and pleasant to walk around during all flight regimes. Stewards will have no trouble serving martinis and meals. Passengers will find no difficulty consuming them. They will just have to drink a little faster. New York will be only a few hours away. Thus, Concords went into service and became a considerable drawcard at airports. However, airlines showed little enthusiasm. The world's other airlines looked to the Boeing 747 jet, a conventional airliner that could carry up to 400 people, compared with the Concorde's paltry 100. But Concords continued to operate, serving a very well-heeled, exclusive clientele who are prepared to pay exorbitant prices to enjoy a whisper-quiet flight and a glimpse of Earth's horizon from 60,000 feet in the air. On the ground, people would often stop what they were doing when the Concorde went overhead and crane their necks for a better look. Although Concorde flights were abandoned following an air disaster in France on July 25, 2000, the great supersonic airliner remains a powerful symbol of luxury and progress. As a publicity stunt, Sir Richard Branson offered to buy the British Airways Concorde fleet for the nominal £1 paid by the airliner when it took possession of the first Concordes. Although the Paris accident was cited as the reason for withdrawing the jets from service, the main reason was a lack of patronage that was making the flights unviable. Where to now for supersonic transport? With subspace passenger travel on the cards, thanks to companies like Virgin Galactic, supersonic flight is back in the spotlight. British company Reaction Engines is researching the viability of a hydrogen-fueled aeroplane that could carry 300 passengers, capable of flying non-stop from Brussels to Sydney at Mach 5+ in 4.6 hours. American aerospace company Aeron has reportedly taken $3 billion worth of pre-order sales on its supersonic business jet. Japan's aerospace exploration agency JAXA has performed a series of supersonic test flights in the South Australian desert as part of its plan to develop a new supersonic passenger jet. A few years ago, the first test flight of a Japanese supersonic jetliner design proved spectacular, but it was not the sort of spectacle its designers had hoped for. A problem soon after the rocket launch to boost the unmanned test aircraft into flight resulted in a costly disaster and a lengthy setback for the multi-million-dollar project. The great supersonic airliners of the past represented a new era and set many records that still stand today. The complexity of their design and construction has rarely been equaled. Concorde remains an icon of aviation history, with British Airways carrying more than 2.5 million passengers between 1976 and 2003. Millions more enjoyed the view of the sleek Delta wing as it soared aloft or glided in to land. Many of these people will be hoping it's true that the return of supersonic passenger travel really is only a decade away.
How indifferent we've become. We've forgotten what it is to be astonished. Another new plane, one more, so what? But there is something unusual about it. It's long and has a sharp snout, and its head is lowered. There haven't been any like this before. And it has a delta wing folded back to the tail. The wing's leading edge is razor sharp. A powerful 4-engine unit is mounted below. And there's another singularity. It has no stabilizer. This is the new Tuvalu supersonic airliner. Take off. Anatoly Agranovsky. Direction, Vermisheva. Director of Photography, Khavshin. A Central Documentary Film Studios production. Andrei Tupolev, now in his 80s, possesses talent and insight to such a degree as to become a living legend. This film is about the Tu-144, his latest model in a long life wholly dedicated to aircraft engineering. When it was conceived several years ago, there were few, even among the top rankers, who believed in its practical realization. They would often get together like this and calculate, design, ponder, and discuss indefinitely.
Предлагается еще процент на 40 уменьшить относительно толщину крыла.
А что мы можем ждать от этого утончения по качеству самолета? Чего 0,2?
Качество, максимального качества. На сколько процентов? Сколько процентов? Это порядка 3%.
They had worked together for years and understood one another at a glance. It's said locally that anyone who can out-argue the general designer can count on a bonus or a promotion. Couldn't the flutter effect appear in your control system? And the body strengthening engineers will see how much metal they must add. I'll do the drawings counting on the body strengthening engineers making their corrections. Get started, and we'll find some time later for a report back.
Тебе надо лазы, шаблоны. Ты усами не прикрывайся, это не поможет.
That will help us arrive at the overall final form. We discussed that question 2 days ago. It's clear now. You finished turning over the finals to Ilyushin so he can speed up his part of the job.
Илюшину окончательные материалы для того, чтобы он мог быстро исправить свои работы.
The model was tested at supersonic speed. And here the character of the streamlining was studied. The Tu-144 required 10 times more investigation in the Great Wind Tunnel than any previous aircraft. This is father and son. Andrei Tupolev has trained hundreds of aircraft designers. He founded a school of aircraft engineering. His son Alexei, chief designer of the Tu-144, has followed in his footsteps. A tailless design was chosen. What would it look like in reality? Tu-144 would have been inconceivable without metallurgists, chemists, instrument makers, and electronic experts taking an active part in its development. New alloys and new kinds of rolled metal were needed. The electronic equipment accounts for half the plane's cost. Some 10,000 parts are made of plastics, so the building of this plane was a common achievement of Soviet science and technology. This is a fighter plane. It flies at the design speed for the Tu-144, 2,500 kilometers an hour, more than twice the speed of sound. So it's nothing new. Our foremost Army pilots have mastered it. What is new, though, is that Tupolev has put this incredible speed at the disposal of ordinary mortals. However, not only the speed, altitude, and distance barriers have been surmounted, but the reliability barrier, too. The landing gear was being tested. What was there about it that instilled confidence? Should the hydraulic system suddenly fail, another backup system would take over, and then, if necessary, a second backup system, and even a third. So one failure is nothing to worry about, and even two failures will not cause a crash. The crew had been pre-selected and had rehearsed the flight over and over again on the ground. Airborne, they wouldn't have the time to recall, waver, or grope. They'd have to make split-second decisions, and that meant they had to know the plane like themselves. Each of them had a college education and lengthy, thorough training for the maiden flight. Commander Yelyan, give us a readiness report, please. First, we'll make the landing gear retraction and release test. I wanted to hear what you have to say about takeoff. We considered Alexei's remarks about reducing the ground run. The shorter the takeoff, the quicker will be airborne. Well, to you who are about to fly, fingers crossed. The maiden flight took place on December the 31st, 1968. Everything had long been in readiness. They'd been waiting for clear skies, but the weather continued foul, and nerves were wearing thin from the strain. Finally, however, the very last day of the year dawned clear. The mercury fell, and visibility rose. Andrei Tupolev had watched 120 maiden flights, and here he was again, waiting. Meet Flight Commander Edward Yelyan, Engineer Yuri Zeliverstov, Leading Test Engineer Vladimir Benderov, and Second Pilot Mikhail Kozlov. Yes, it was a fine day indeed. It was good to be alive on a day like that, as a well-known test pilot put it. This is Dolphin 1 ready to take off. Permission granted. Got you. Some compare it to a bird, for a bird never takes wing with its head drawn back. The plane took off and gained altitude. There was nothing left for us to do but watch and wait. Nothing depended any longer even upon the general designer. Mr. Tupolev, how did you begin? I matriculated at Moscow's higher technical school because I had a bent for engineering. Our lecturer on aviation was Nikolai Zhukovsky. We built the first glider, and I made my first flight. When Zhukovsky decided to set up an aerodynamic laboratory at the school, he said that Tupolev had clever hands, so he would be in charge of the equipment.
Руки хорошо работают. Вот мы, говорит, его и назначили заведующим оборудованием лаборатории по авиации.
Actually, there wasn't any laboratory at all, simply a big hall the school allotted us, and that's how it all began.
Когда же пришла революция, то мы, около Николая Егоровича Жуковского, был уже тесный кружок людей, которые, приходя к нему,
when Soviet power came, Nikolai Zhukovsky had gathered a close circle of people dedicated to aviation.
на всю жизнь. И мы хотели всей группой вместе
We all wanted to help our Soviet country.
нашей уже советской России.
Tupolev has advanced through nearly every stage of aviation. He even recalls planes of plywood. He built the first all-metal aircraft. This is one of them, the ANT-3. ANT are his initials. And another, the Maxim Gorky, at that time the world's biggest. And this is the ANT-6 at the North Pole. The famous ANT-25's non-stop flights won world acclaim. It took Chkalov 63 hours to fly non-stop from Moscow to the United States. This is a Tupolev heavy bomber taking part in a landing operation. The war over, the Dean of Soviet aircraft designers again produced projects which could be classed among the boldest. The Tu-104, flagship of the Soviet Civil Air Fleet. Tupolev ushered in the jet airliner era, and now he's hurtling us beyond the sound barrier. The flight continued. Now the plane raised its head. For supersonic flight, it needed a long, pointed nose. So far, so good. Everything was proceeding normally. I've stopped climbing. Everything on board is tip-top. The craft handles with astonishing ease. Now I'm banking for the first time. The ground is visible. We've finished the maneuver. Now we're going to fly over. Have a look at us from down below. How does she look? Not bad, huh? Leo Tolstoy once wrote a story told to him by an aeronaut. The first minute I was terrified. My blood turned to ice. But then all of a sudden I felt such a joyous uplift that I forgot all about being afraid. And we'll forget to be afraid too. In 3 hours and 20 minutes, we'll fly from Moscow to Khabarovsk. In 2 hours, from Delhi to Moscow. Outstripping time will become habitual. We'll take off from Moscow at noon and land in Montreal at 9 in the morning of the same day. We enter the plane, walk down the nylon carpeted aisle, and settle in a soft armchair. Smiling air hostesses will come forward to greet us, and in all probability, no one will remember anything about those who built this airliner for us. There are 300,000 meters of wiring alone. Of course we won't remember. It's enough for us that there is no noise, no vibration, no pressure drops. That at a 20-kilometer altitude, there are no thunderstorms or clouds, and that fares remain the same. Meanwhile, the flight continued. The airliner embodies all that is best in world science today. There is a computer center on board. If the flyers overlook something, the clever machine will remind them. Besides a sign flashing on, they will hear a voice saying, "Switch over the radio beacon," or "Release the landing gear." I'm coming in for a landing. Now the aircraft had lowered its head, for the flyers need a good all-round view for landing. This was not simply another new aircraft heading home. It was a new history-making stage in world aviation. It was over. The flight had taken 38 minutes. In that time, the plane could have flown from Moscow to Simferopol. These people can rejoice. RTU-144 was the world's first aircraft of its kind to take off. This was only its maiden flight. Tests and trials will continue.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks' Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the DroneScapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.